I see this as the core question. We're exploring how the number of nearest neighbors considered when building a graph influences the final data representation, embedding, created by spectral embedding. Think of it like this. A larger neighborhood means a broader view, while a smaller one focuses on local details. Imagine if you consider every point as a neighbor for each point. The graph becomes completely connected, losing all shape or meaningful structure. The embedding then becomes uninteresting, all points clump together in the center. That's what we mean by a trivial embedding. It's like trying to find distinctive features in a completely uniform blob. If I increase the number of neighbors, the resulting graph becomes denser, connecting more distant points. This gives a smoother, more holistic representation of the data in the embedding. It's like increasing the scope of your vision. Conversely, reducing the number of neighbors produces a sparser graph. This emphasizes local relationships because points will be connected only to a very few of its closest neighbors. The embedding will show distinct clusters, each representing a tightly knit local neighborhood. It's like zooming in on the fine details. This statement is wrong. I've just explained how this parameter drastically impacts the graph structure and therefore the resulting embedding, right? This parameter is crucial and the results are very sensitive to it. I'll explain. KNN graph construction. In simple terms, imagine you have a bunch of data points scattered around. The K in KNN stands for the number of nearest neighbors. N_neighbors in Scikit-learn's spectral embedding is this, K. For each point, I find its N_neighbors' closest points and draw a line connecting them. This forms my graph. A small N_neighbors means a sparsely connected graph, showing only close relationships. A large N_neighbors means a densely connected graph, encompassing broader relationships. This question dives right into how the number of neighbors you consider in spectral embedding affects your final data representation. It's like asking how changing the zoom level on a map affects how you see the details of the area. Spectral embedding is a technique to reduce the complexity of your data, while trying to preserve its structure. Think of it like creating a simplified map of a complex city. The goal is to keep the important streets and landmarks while making it easier to understand. The N_neighbors parameter is super important because it controls how you connect the points in this simplified map, influencing the final layout. I see what's happening. If you increase N_neighbors too much, almost every point becomes connected to every other point. The graph becomes dense and meaningless. Think of this like connecting all the houses on a city map directly. The map would lose all sense of local neighborhoods. You'd just see one big blob. That's what I mean by a trivial embedding. All the points bunch up in the center, losing their individual identities. When you decrease N_neighbors, you focus only on local relationships. Your resulting embedding might have separate, distinct clusters since only nearby points are connected. Think of a map only showing roads within a small neighborhood. You'd lose the big picture but highlight local structure. Increasing N_neighbors creates a more connected graph, connecting points farther apart, creating a smoother embedding that represents the global relationships. Think of a map showing all highways in a region. You get a smoother representation of major routes and the overall connectedness of the area. I see this as the title of the problem. We're exploring how changing the number of neighbors affects the results of a dimensionality reduction technique called spectral embedding. This introduces the core question. How does changing the number of nearest neighbors influence spectral embedding's output? This is the heart of the quiz. We're looking at the Scikit-learn library's spectral embedding function and specifically how one parameter, N_neighbors, affects the results. N_neighbors determines how many of a data point's closest neighbors are considered when creating a graph used in spectral embedding. I'll break it down step by step. I think this option is correct. A larger N_neighbors value means each data point is connected to more neighbors. This creates a densely connected graph, leading to a smoother embedding where distant data points are better connected in the reduced dimensional space. I agree, this is also correct. A smaller N_neighbors value creates a sparsely connected graph. The embedding then emphasizes local clusters because only nearby data points are connected, highlighting small, localized groupings. I disagree with this option. It's incorrect. The _n_neighbors parameter is crucial because it directly shapes the graph used in the algorithm, so it significantly impacts the embedding. I think this is correct. If _n_neighbors is too big, almost as big as the total number of data points, the graph becomes very densely connected, which basically means everything is connected to everything. The algorithm loses the structure of the data, resulting in all the points collapsing together in the reduced dimension. That's a trivial embedding, not useful. I'll explain how the number of nearest neighbors affects the final data visualization. A small number focuses on local details. Think of magnifying a tiny section of a map. A large number shows the big picture, like looking at the whole map. But a number that's too big might blur everything together, making it hard to see individual spots. This is because spectral embedding uses a graph, where each point is connected to its nearest neighbors. The number of neighbors directly impacts the graph's structure. I'm asking how changing the number of nearest neighbors affects the way spectral embedding squeezes high-dimensional data into a lower dimension, like from 3D to 2D for visualization. Think of it like shrinking a complex object. The result depends on how you do the shrinking. If I increase the number of neighbors considered, the resulting picture will be smoother and more connected because the algorithm considers broader relationships between data points. If I decrease the number of neighbors, I'll get a picture that emphasizes local groups of points, showing clusters more distinctly. That's wrong. The number of neighbors is very important and significantly affects the outcome. If I choose too many neighbors, all the points will clump together in the center, making it uninformative. The connections become overwhelming, losing important structure. I'll explain the key steps of spectral embedding for dimensionality reduction. First, I build a graph where each point is connected to its k nearest neighbors. K is the n_neighbors parameter. This parameter controls how many nearest neighbors are considered in building the graph. Think of it as the reach of each data point. I calculate a graph Laplacian from the KNN graph. This is a matrix representing the connections in the graph. I find the eigenvalues and eigenvectors of the Laplacian matrix. The eigenvectors represent new coordinates in a lower dimensional space, where I project my data points to get a lower dimensional representation. The final output, the data now reduced to fewer dimensions, after undergoing the spectral embedding process. I see this step as creating a network. Imagine each data point as a person at a party. The _n_neighbors parameter sets how many closest people each person can talk to. A small number means only a few close conversations, while a large number means lots of interactions, potentially with people far away. This is the magic step where I use information from the network to place these people, data points, in a lower dimensional space, like a 2D map. The goal is to maintain the relationships between them from the original higher dimension. This question asks how the number of connections I allow in the party, the _n_neighbors parameter, changes how I arrange everyone on the map, the embedding. This refers to a technique I'm using, SpectralEmbedding, that's highly influenced by a parameter called _n_neighbors. I use it to reduce the complexity of my data. Think of it like summarizing a long, detailed story into a short, impactful summary. _n_neighbors is just a variable, often represented by k that decides how many closest neighbors each point connects to. It's like deciding how many people each person can talk to at the party. This is the final result, a simplified representation of the data, kind of like making a map. Each point is placed on this map to maintain its relationship with others. It is a lower dimension that retains relationships between points. Think 2D map instead of a complex 100D space. These are the individual pieces of information I'm working with. Think of each data point as a single person at a party. I want to understand how these people relate to each other. This is a mathematical tool that I use to analyze the network of connections between points. It helps to translate connections into a form suited for my map making. It basically looks at all connections and uses its structure to make the spectral embedding. I see the term KNN graph. That stands for k-nearest neighbors graph. Think of it like this. We have a bunch of data points, and for each point, I find its k, which is the value of n_neighbors, closest neighbors. Then, I draw a line connecting them, creating a network or a graph. This network is crucial in spectral embedding. It dictates the connections between points, informing how the points group and cluster together. Spectral embedding, with its NNEIGHBORS parameter impact, is all about finding the best way to arrange our data points in a lower dimensional space while preserving their relationships. We use a graph to capture those relationships. A key decision in this method is choosing how many neighbors to consider for each data point. That is where n_neighbors comes into play. It impacts the final arrangement. This is a multiple-choice question about the effect of changing this n_neighbors parameter in spectral embedding. It looks at what happens when you increase it, decrease it, or make it excessively large. Essentially, it tests how well you understand how this parameter affects the overall shape of the result. I'm going to explain each option in simple terms. An excessively large n_neighbors value makes the graph too interconnected. Imagine a social network where everyone is friends with everyone. You lose the unique clustering and the data points become less distinct in the embedding, essentially collapsing toward a central point. This creates a trivial embedding that loses the rich structure within the original data. We want to avoid this. I'm posing this question because it is crucial to understand how the choice of the number of neighbors affects how spectral embedding works. We are not just playing around with parameters, we're trying to understand the mathematical basis. The behavior of spectral embedding is directly tied to how we define the connectivity of our network.